pray the marker doesn't run out.
If it does, I have one.
Cool. So we'll finish, or we'll start with another example of graphing.
Oh, that's good.
That was fun. And then,
Will it make a flower design this time?
no, not so much of a flower. Then we need to do a little bit, just a little teeny little bit of topology, which is nice.
Which will be expanded next semester, right?
Perhaps, yes. I'm in negotiations to teach topology. It doesn't matter if you know what topology is. We're only going to need one teeny little definition from it. And then we're going to jump in to limits. And
I read the course description once and it sounded really interesting. And ever since I've been on
limits and
this
derivatives.
Wait,
Yeah.
are you really trying to make a class with topology
I know.
next semester?
Differential equations and topology. Those are the two I'd like to teach.
And I want to take those two.
differential equations. You wouldn't be willing to have like a night class, would you?
No, I think.
Alright, forget it then. I can't do it.
Why?
Because I'm going to be student teaching. I'm going to be in school all day.
What are you supposed to take classes?
Student teaching is 12 credits. So that's like my semester.
I apologize.
You guys take the 4 o'clock class.
Well, we can do an independent.
No, I can do like an evening class. That's fine.
All right. So I'd like to.
Too high.
Too high. I
So
gotta
then
be too
tilt
high.
the camera.
You gonna move it back a little bit?
This is more back, so let's go.
We'll move the table. This is a heavy table. I got my feet on the wall and everything.
I have a question.
Yep.
Does everything that you do, like between class that gets recorded, go on, or do they like edit some things? Like,
Well, we don't. This conversation right now will be on the tape. Yeah. But the stuff at the very beginning usually gets edited
so
out.
you pushing your table will be on the table.
Yeah. That's right.
Excellent.
Okay. So, if you recall, last time we graphed z squared. W equals z squared. That was the last thing we did. And the thing is we didn't want to graph all of the complex plane getting mapped via z squared because you would have just ended up mapping the entire complex plane to the entire complex plane, which wouldn't have been very interesting. Okay, so this time we want to graph e to the z. And again, we don't want to graph, I mean, Well, just the norm of e to the x. But e to the x is just a real number. Right? And so the norm isn't doing anything because it's not just a real number, it's a, I mean, what's e to the x? It's always a positive real number, right? When you take the norm of a real number, it's the same as taking the absolute value. The absolute value of a positive number is just itself. So you actually just get e to the x. Okay, so the norm of e to the z is just actually e to the x. Okay. So, what's going to happen as you move along this line to the norms of the elements? So, if you're at this point here, this looks like a plus ci. According to this formula, the norm is just actually e to the a. Right? Right? When I move, not the norm of this point here, but actually under this transformation, the norm will be e to the a. And what if I move up along this line? What happens to the norm?
It's bigger.
Not to the norm of this point, but to the norm of e to this point.
It stays the same.
It actually stays the same. Why? Well, this tells you that if you take e to the z, right, where z is x plus iy, then the norm is just e to the real part of z. But look, as you move along this line, the real part of z doesn't change. So the norm of e to these points is the same number. The norm doesn't change. So, and the same thing happens if you pick any line going across here, right? Any vertical line, along this vertical line, the norm stays the same. Now, a is smaller than b, and so what's happening is that e to the a is kind of the smallest radius, or the smallest norm you get. E to the b, then, is the biggest norm that you can get in the image. And then everything in between is, well, some norm in between. So let's draw a circle.
Wait, I'm confused.
Yeah.
Never mind.
Okay.
Are we making a donut?
Sort of, but not quite. Okay, so this circle here is e to the a. And, well, put a circle over here. Okay, and that'll be size e to the b. So everything has to live in this ring. Okay, because the norm has to be between e to the a and e to the b. Okay, so now the question is, where does it live? Well, the angle that you get is determined by this y. So it's the y, right? It's this height here. I haven't used that yet. Now, what should be the case is that if you make this bigger, then you should go further around the circle. And if you make it smaller, then you should go less around the circle. Without telling you what C and D are, I can't graph exactly what they're going to be. Right? But what we can say is that, well, it's going to be some sort of sector of this. Okay? And it depends on what my values of C and D are. But we know that it's continuous, so it's going to map out some region of this. So that's as precise as we'll get. Okay, so this is the graph. This strip turns into this little sector. Okay. So just wanted to give you one more example of how you might think about these things. In the book, there are several examples you can read about how you can take some region, take a function, and then try to suss out what the picture has to be. It's not as straightforward as plotting points has a lot more points to plot. But you can think about this. Okay, so I don't want to use that. I want to start over here. So now we do a little bit of topology, but not a lot. In fact, if you've taken a course in real analysis, you really already know this definition. Only you know it for the real numbers or the real plane, and we're going to do it for complex numbers. So let's let, I don't know, say D be a subset of the complex numbers. Okay, so we better have a picture at all times. So there's my complex plane. Okay, and here's D. Some subset, no problem, right? It's just some collection of points. Now let me choose a point in here. Let's call it Z. Let me draw a little circle around Z. And actually, now, I'm going to try to write this down precisely for you. So let me actually call this Z naught, right? Z sub 0. Just to differentiate it from the variable Z. So this is a nice circle. It has a radius. I need a good name for the radius. So let me call this radius epsilon. So I'm going to call this little ball here, this that includes the 0. I'm going to call this an epsilon ball. So when I say epsilon ball, this is what you should have in your head. Okay, it's just a circle, and really a disk, around your point Z0 that has radius epsilon. Fine. The question that we want to answer is, if I pick this point Z0 and I put an epsilon ball around it, are all the points within that epsilon ball inside of my set D? For instance, over here I have a nice epsilon ball. Every point in that epsilon ball is inside D. No problem, right? What if I choose a point over here? Can I put this same epsilon ball around this dot and have it all be in D? Well, no, right? Because if I put the same size one, it looks like that maybe, and it goes outside. But, well, I don't really care about keeping the same size. I just want to make sure there's some epsilon ball. Right? So, okay, so I have to make it a little smaller. Okay, so there's a nice epsilon ball. It's a little small, it fits inside. What if I choose a point here? Can I put an epsilon ball around it that's all within D?
That's on the line.
Yeah, it's on the line. There's a problem here, right? If you try to put this epsilon ball around it, no matter how close, how small you make it, right, you're always going to have to go outside of the region. Okay, so we want to differentiate between subsets D, where you can put an epsilon ball around every point, and those where you can't.
So epsilon cannot be 0?
Not allowed. Epsilon's not allowed to be 0. Epsilon's always greater than 0. Okay, so
Open plus closed. That's all we're going.
that's where we're heading for. So D is an open subset of C if for every Z0 in D there exists an epsilon ball around Z naught in D. So in D meaning the whole epsilon ball is completely contained in D. So this is an open subset, right? Or sometimes we'll just say an open set. So the first question is, how can I make D into an open set? All right, what's the problem with D?
Closed.
It's closed. Why is it closed, right? Well, I haven't told you what closed is, but the problem, right? Well, all these points in the middle, there's no problem with those, right? I can stick balls around those. The problem is the boundary of the set. So what if I just get rid of the boundary, right? What if I do the little dots? Okay, so I'm not allowed to take these points anymore because they're not actually in the set. My kid would love this. So now I'm not allowed to use any of these points on the boundary, right? So now I can get as close as I want to the boundary, but not actually go on this boundary. And then you can make a really tiny epsilon ball, and you're completely in D. Okay. So that's what you want to. That's what you could do. Okay. So we just need this definition. There's a few technical things that we're going to have to write down, and you need to at least know what an open set is. By the way, we won't need it, but a closed set is one whose complement is open. What's the complement of the set, right? Well, take all the complex numbers, choose some subset. Okay? Now, every point is either in the subset or out of the subset. You're in or you're out. The complement of this set is all the stuff that's out, which is itself another subset. So, a set is closed if you look at the complement, and the complement is open. That's all. That's how you can differentiate between closed and open. Okay, but I'll save any more for classical topology. Okay, so we just needed that. Okay, fine. So now we can start limits and derivatives. So, okay, good, I didn't skip anything. So let's say we have a function, f of z, and I want to know what I mean by taking the limit as z goes to, say, z naught. Okay, of course, it should mean what we all think it means. So if this is supposed to equal some number, say delta, I don't like delta. We like to use delta for other things. Let's use gamma. Gamma doesn't get used enough. What do we mean by this? What is the limit? What's it supposed to mean from calculus? And this point z is a complex number. Okay. And it's getting closer to a fixed complex number z naught. And as it gets close, f of z should be getting close to the number gamma, which is also a complex number. Okay, so how close? Well, and is it? What is it? It has to get close. Stay close. You know, my kids are trained for this. You say it has to get close and stay close. What does that mean? It means if for any epsilon greater than 0, okay, this is how you're estimating how far away f of z is from gamma. You're saying epsilon greater than 0. There exists a delta greater than 0, such that if z is within delta of z naught, but we're not allowing it to actually equal z naught, then f of z is within epsilon of gamma. So let's draw a picture for that. What's that? This should look familiar.
It is.
This should look just like multivariable calculus, only now, remember in multivariable, when you drew this picture, you put down R2 on the left, and then you just put down the real numbers on the right. And here we actually have to put down 2 copies of the complex numbers. Okay, so you have some point, Z0, and then you have the complex number gamma over here. And what this definition is saying is, okay, this limit exists and it equals gamma if for any epsilon ball, around gamma, you can find a delta ball around Z naught. So that if you put your Z within that delta ball, okay, but not equal to Z naught, then this thing will get mapped via F into this epsilon ball. Right? Which you're really drawing going all the way in. It has to go all the way in. Okay? That's the point. You start on the right with an epsilon ball. Then you should be able to find a delta ball such that the entire delta ball, sans perhaps Z naught, gets mapped into this epsilon ball. Okay? We don't actually care what happens at Z naught. A little hole in there actually. You guys happy? You guys happy? It's not a metaphysical question. So what should the definition of continuity mean? So, F is continuous at Z naught if, well, it's the exact same condition as we had for real variables. If the limit as Z approaches Z naught of f of Z equals f of Z naught. If you can evaluate the limit by simply plugging in Z naught, then the function is continuous at that point. Okay, which, again, the physical interpretation of continuity is that a small change in the input results in a small change in the output. Or if you're drawing the picture, you don't have to pick up your pencil. Or paintbrush, so now we're in 2 dimensions. Okay, so we have continuity. So first you do limits, then you do continuity, and then you do derivatives, right? That's next. So, let's let Z naught be a complex number. And assume that f of Z is, let's see, I want continuous. I think or I don't even need continuous, I just need defined. Is defined on an open set containing Z naught. So, well, here's a good question for you. If I just take the point Z naught, just one point by itself, is that an open set?
Oh,
If I take the one point, z naught, just a point right there, is that an open set?
isn't it both?
Isn't it both?
Can it be both?
Open and closed. By the way, some sets are neither open or closed. That can happen also. Well, let's see. What is the definition of open? It means for every point in the set, you can put an epsilon ball, which by, as Kaiway asked, it cannot have a radius 0. It has to have positive radius. There's an epsilon ball around that point, which is completely in the set. So can you put an epsilon ball around this point, which is entirely in that set? Well, any epsilon ball looks like this. And of course, it contains more than just that one point. So the answer is no. So when you say, so this is going to be the start of the definition of a derivative. Right? We're assuming that your function is defined on an open set containing z naught. It can't just be defined at z naught. Okay? It doesn't make sense to define the derivative at this point if the function is, say, only defined at z naught. We really need it to be defined in some area around z naught. Okay. So we assume that there's you have some ball around z naught and the function is defined on it. Okay, some nice open set. It doesn't have to be a ball, it just has to be an open set. The derivative of f at z naught is, now this is going to surprise you. It's the limit as, well, I don't want to use h. Let me use something closer. Let's say delta z, right? Small change in z. It's the limit as delta z goes to 0 of f of z naught plus delta z minus f of z naught divided by delta z. This looks completely different than anything you've ever seen. Because in all the other examples where you've seen derivatives, those were x's. This is the derivative, right? It's exactly what you've seen before, right? There's nothing new. This is really quite nice. Okay? Except for one thing. What's the only difference? Well, like I said, before they were x's. Now these are all z's, right? In some shape or form. This delta z going to 0. The important thing is it can go to 0 from a lot of different directions. This is some small z, and it can go this way, and go this way, and go this way. Okay? Which means when you compute this limit, again, there's a lot more limits to check to agree for this limit to exist. And then when we did the real numbers, these epsilon balls and delta balls, they were just little intervals. Now they're big circles. Okay, so but in any case, this is the derivative. So maybe we should compute one. Okay, so let's compute one for a function which is quite simple. Let's compute the derivative of f of z equals z bar. This is not missing a numerator.
Oh, darn, it would have been so easy if it was 0.
Okay. So to compute this, we need to, well, evaluate the difference quotient, just as we always have, right? You take the limit as delta z goes to 0 of, well, let's see, f of, well, we don't even put z naught here, right? We just put z. F of z plus delta z. That means you have to do z plus delta z bar. Right? That's the first bit. Then you have to subtract. Since we're doing it at z, it just becomes z bar, and then we divide by delta z. Now, as you guys ascertained, I said explicitly once in class, Complex conjugation is a ring homomorphism, so you can break it up on the sum. So this becomes the absolute, or rather z bar plus delta z bar minus z bar. And of course what happens, the z bars cancel. So you're just left with delta z bar divided by delta z. You look skeptical.
Yeah.
Remember, when you have a bar, you can break it up on a sum. So this is z bar plus delta z bar. And then you also have minus z bar. So z bar minus z bar, they're gone. So then I'm just left with delta z bar divided by delta z. Okay, now we have to evaluate this quotient. Delta z, we have a lot of options, right, for how it can go to 0. For instance, what if we just let delta z be some number that's moving along the real axis? Right? So it looks like 5, 4, 3, 2, 1, a half, a fourth, an eighth, a 16th, right? It's getting close that way. When you take its bar, this is just some number moving on the real axis. It's a real number. When you bar a real number, it's just the same number, right? There's no imaginary part to conjugate. So this bar would just go away, and you get delta z over delta z, which is 1. Okay? But what if we, instead of moving along the real axis, we move down along the imaginary axis? 5i, 4i, 3i, 2i, 1i, I over 2, I over 4, I over 8, I over 16. Now when we bar it, it becomes minus, right? I over 2, when you bar it, it becomes minus I over 2. So then you can get rid of the bar by putting a minus. So you get minus delta z over delta z, which is minus 1. So does the limit exist? No, because if you come one way, it's 1. If you come another way, it's minus 1. So this limit does not exist. Which means this function doesn't have a derivative. So simple. And it doesn't even have a derivative. Right? I mean, that's anywhere, right? This is not dependent on z, really. This is really bad. I mean, you think about it, the only problem we ever had in the real numbers with derivatives not existing was the absolute value function. And that was only at 0 that you had a problem. This is already much, much worse. What this example is going to tell us is that it's harder to be differentiable as a complex function, but it's going to be more valuable to know that it is differentiable. Okay, I think we can move on to the... Oh, I should define this one thing before we do it. So this is a definition that's going to give you a word that is probably the most important word in complex analysis. So if
Is that the word?
F is analytic, on an open set D of complex numbers, if F is differentiable at all points in D. Okay, so it's just a new word to mean differentiable. Say it's analytic. Sometimes it's also called holomorphic. We're going to say analytic here. So, a first approximation of complex analysis is that you want to study analytic functions. This is not the end of the story, but it's at least a good beginning of the story. So the next thing we want to do is try to determine when a function is analytic on an open set. We want to give a criterion for deciding when it might be. right? Or even better, saying it's not for sure. And the criterion is going to be something called the Cauchy Riemann equations. And they're going to be surprisingly easy to produce, but incredibly powerful. Yeah, so Cauchy was a great mathematician before he got married. Then he got married and he became Cauchy Riemann. He took his wife's last name.
No, he's not.
That's a joke. No, there are two mathematicians, Cauchy and Riemann.
They were married?
They were married. Granted, I'm not sure they lived actually at any point at the same time, but
How could they come up with a bunch of equations?
so how are the equations going to work? Well, we have to go back and remember something we did last week, which was if you have a function c to c, and we saw that it's going to eat some z, and then it's going to spit out a w, right? But we could break that w up into its real part and its imaginary part. And the real part was completely dependent on x and y, where z here is x plus yi. And the imaginary part is another function completely dependent on x and y. So a way of writing this function f, right, is to view it as really two functions, u and v, which are actually functions of two real variables. Okay, so let's go back and try to rewrite the definition of the derivative with the u's and the v's instead of just with the f. So let's see, what if we take, instead of, well, I mean, we're going to look at some delta z going to 0, but let's just move along the x-axis. Okay? So instead of calling it delta z, to tell you that I'm moving along the x-axis towards 0, I'm going to use delta x. It doesn't matter what I call it. I'm just telling you this is something going to 0 along the x-axis. Now the f, this f has two components. It has a u component and it has a v component. So the u component, right, so again, z I can write as x plus yi. It eats x plus, well, the delta z, right, is now my delta x. Okay, so I'm just changing the x coordinate. And the y coordinate is staying fixed. Okay, as I move along the x-axis, right, the real axis, my imaginary axis isn't, that number isn't changing. Okay, so this is the u part. And now I need the v part. So again, the v part, the x is allowed to change, but the y stays fixed. And then you get this I. Okay, so I've just rewritten f of, well, I've replaced z naught here, which is the z, and then z is x plus iy. Just rewritten it using this notation. This is just the first bit. I haven't even got to the minus sign. Now I need to put the minus sign. Now the minus sign is much easier. Now I just have to evaluate f at z, right? But now evaluating f is the same as evaluating these u's and v's at x and y. So this is minus u of xy plus, but this minus makes it another minus v of xy I. Okay, so this part here corresponds to the f of z plus delta z, and this part here, right, with the minus signs appropriately put as the f of z. And then I have to divide by delta x. Alright, well, it is what it is.
But that's just, you have to do another one for y, don't you?
Have to do another one for y as well. Yep. Why? Yes, why?
We know, but why?
Now here's what I'm going to do. I'm going to take this mixture of reals and imaginaries and split it up, okay, into reals and imaginaries, right? I'm going to partition things. I'm going to segregate. Okay, so the first bit, I'm going to put this u and this u. So this bit, when I'm just doing the real part first, I get u of x plus delta x comma y minus u of x comma y divided by delta x. Plus, and you won't be surprised to know that the limits can be split up. The limit as delta x goes to 0. Well, now I do the v's, and this I is just a constant, so I can pull it out. Let me pull the I to the front, and I get v of x plus delta x comma y minus v of xy over delta x. Okay, now you guys will be forgiven if you don't know what this is, because it's been a while since you took multivariable calculus, but you guys over here should know exactly what this is. A partial derivative.
Sounds familiar. Yeah.
This is the partial derivative of u with respect to x.
So it's like f sub x.
Exactly. So how about we call it u sub x?
Cool.
Partial derivative, right? You could also write this as say the partial of u with respect to x. Okay, but I like u sub x. That's this part. Put that in parentheses so we know it's just a. Okay. Plus, let's see, we have an I times, what is this? Well, that's just partial derivative of v with respect to x. So it's just v sub x. Okay.
Let's see.
Now, we have to do the same thing for y. You might stop me and say, well, wait a second. Why are we going to write this whole thing down again?
Why?
X and y are pretty much symmetric in the problem, right? So shouldn't I just be able to write down everything the same but with y's instead of x's? And the answer is almost. 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 But you see, we're trying to do things, we're trying to bring things back somehow into the real world, right? Other than this I sitting out front, everything here that you're seeing, right, is a function of two real variables. And if you want to do that, for instance, this number down here should be a real number. So, well, to do this with y's, we'd want to move, of course, along the y-axis, which corresponds to the imaginary axis. So, yeah, these delta y, if you want delta y to be going to 0 as a real number, this down here, though, that's supposed to be on the imaginary axis. It actually needs to be I delta y. Because that's how much you're changing. You're not changing by a number in the real direction. You're changing by a number in the imaginary direction. So, okay, so we'll write this down quickly, though, because once you make that observation, it's not so hard. All right, so limit as delta y goes to 0 of, okay, so it becomes u of, now you have an x, and you're changing the y. Okay, but in the I direction, plus v of x comma y plus delta y in the I direction, minus u of xy minus v of xyi divided by I delta y. Make sure I didn't mess anything up there. Oh, of course I did. You can't put these i's there. We want things to be, those i's on the inside, you don't want to be there because we're supposed to be moving. These are all supposed to end up being real functions. So those are really moving in the y-axis of the real plane. Okay? So again, we break this up into real parts and imaginary parts. Okay, so the first one, you get u of x comma y plus delta y minus u of x comma y over, well, now you get I delta y. And then the limit as delta y goes to of v of x comma y plus delta y minus v of x y. And there should be, oh, the I should be up here. That's where the I should be. I over I delta y. Phew.
That's easy enough. The eyes all cancel now.
Yeah, on this side, right, the I, you can factor out an I and then it cancels. That I. But over here, you're not so lucky. There is this I. Now you can pull it out, and it becomes a 1 over I. Now how can you simplify 1 over I?
Negative I.
It's just negative I. Now why is that? Let's just do a little side one.
Because it's I to the negative 1, which is the same as I to the third.
That's true. That's a reasonably good way to think about it, right? I to the minus 1, which is what this is the same as I to the third, correct? Because you can always shift by powers of 4. Right? Is that right? Okay, and I cubed, right, is I squared times I squared, okay? Or you could just say, well, multiply top and bottom by I, and you get I over I squared. But I squared is minus 1, so I over minus 1 is minus I. In any case, it's minus I. So you can pull out this 1 over I, and it just becomes a minus I. Okay, so minus I, and then you're left with this limit where the now, well, it's just the partial derivative of u with respect to y. So minus I uy plus, well, like I said, like Christina pointed out, you can cancel these i's, right? Factor an I out and cancel. And so this is just the partial of v with respect to y. So vy.
So the u function now becomes the I part.
Yep. So if we rewrite this so that it's in the correct order, it's vy minus I, or let's put the I last, minus uy I. Okay. So we now have the Cauchy Riemann equations. What are the Cauchy Riemann equations? Well, we've computed the derivative in 2 different ways. If the derivative is going to exist, it shouldn't matter what order or what way you compute it. Okay? Whether you come along the x-axis or along the y-axis, you should get the same derivative. So we can say for the derivative to exist, we must have the 2 answers equal each other. So we must have ux plus ivx equaling vy minus, oh, I put the I on the other side here. Ux plus vxi equals vy minus uyi. But you can go even further than this. And you can say, yeah, but if you have these things defined this way, certainly when you have complex numbers, if they're going to be equal, the real parts have to be equal and the imaginary parts have to be equal. So this means that ux has to equal vy, and vx has to equal minus uy. And these are the Cauchy Riemann equations. So if you're going to be differentiable, you need these whole Cauchy equations. Is that clear? Cool. Let's see. I think I had a good example plan for this. Yeah. Let's define a function w equals x plus y squared I. So that means if you know what the z is, it looks like x plus yi, then you just take x add y squared I, that's your function. Okay, so I want to know if this thing is going to be differentiable anywhere. Okay, this looks pretty easy, right? You should be able to take derivatives of something like this. Well, we're going to check the Cauchy Riemann equations. First, what's u? U is just, right, it's just the real part of the function, so it's just x. And what's v? It's the imaginary part of the function, so it's y squared. If this is going to be differentiable anywhere, we need the Cauchy Riemann equations hold. So we check these partial derivatives. So ux equals 1, uy equals 0, vx equals 0, right? Because there's no x's. And vy equals 2y.
Do you mind just explaining that again? I don't.
How I'm getting these?
Yeah.
Okay, so I'm taking the partial derivatives
Right.
of these functions with respect to x. So, for instance here, well, the derivative with respect to x is just 1.
Oh, right. Okay. Yeah.
But with respect to y, it's 0 because there's no
Okay.
y's,
Yeah.
right? X is a constant with respect to y. Okay. So, for the Cauchy Riemann equations to hold, we need that ux equals vy. Well, let's see. 1 equals 2y. So Cauchy Riemann would imply that 1 equals 2y, which of course would mean that y equals 1/2. And, well, vx should be minus uy. Well, that's 0 equals minus 0. That's no problem. So the only way the Cauchy Riemann equations can hold is if you're on the line y equals 1/2. Okay, which, well, what does that mean? Well, the y, right, that's corresponding to the imaginary part. So you must be on this line. Okay? So, does this say that the function is differentiable on this line?
Yes.
Well, there's a couple things, there's a couple clues here. First, when I write for the derivative to exist, this is saying I'm setting up a necessary condition,
Necessary, but
not
sufficient.
sufficient. Okay? This is an important set of phrases in mathematics. Necessary, sufficient conditions. Necessary is something that it needs to happen, right, for it, say, to be differentiable. Sufficient means if you have it, you're guaranteed it's differentiable.
Honey, I learned that in government class.
Yes, this is important. That's not just in math. But we use it in math quite a bit. Yeah. Okay. Well, it's kind of like when my kid wants dessert. It's a necessary condition that he eat his vegetables. It is not a sufficient condition, however, because I also want him to eat his meat. So, it also, the other condition that he needs is that we actually have dessert. Okay, so if you're on this line, then you do satisfy the Cauchy Riemann equations, but that does not guarantee differentiability, right? You just know that anywhere off this line, it can't be differentiable. Okay? Now we can actually answer the question though: is it differentiable on this line? Well, let's go back. What did it mean? How did you have a derivative? Well, you needed to have a function, and you had to have a point. The function was defined, but not just at that point, but actually in an open set around that point. Well, let's pick a point on here and say, okay, is it differentiable there? Well, if it's differentiable there, that means that the function is defined on an open set around that point.
No.
And it's differentiable there. Well, yeah, exactly, right? Okay. I can only get differentiable on this line, so certainly not. You end up being differentiable always in an open set. And this, right? You can't put an open set around this point that's only on this line. Because any open set around it, right? Any epsilon ball is going to go off the line. So, really, the Cauchy Riemann are a necessary but not sufficient condition. Okay, so what? Can I tell you that now? I want to see. I don't want to get this in the wrong order. Yeah. Skip that for a second. I think I'll skip it. I don't like doing that there. Yeah. Yeah. Let's do this example. This is better. Okay, so here's another example where let's assume, right, f is given as u plus vi, right, in the usual sense that we've meant today. And that u is a constant. It's just a real number. It doesn't matter what you put in for x and y, it always spits out the same real number. My question is, can this function be analytic on any open set? Well, let's see. What is ux? It's 0, right? U is a constant, so the derivative with respect to anything is going to be 0. So ux is 0, and of course uy is 0. Okay. Now, if this function is going to be analytic on some open set, then it needs to have the Cauchy Riemann equations satisfied on that set. But if the Cauchy Riemann equations are satisfied, then ux equals vy. If ux equals vy, then vy is 0, because ux is 0. Now, if uy is 0, well, also the Cauchy Riemann equations tell us that vx is negative vy, which means that vx is negative 0, which is 0, so vx is 0. So v is a function of x and y whose derivative with respect to x and y are both 0. What kind of a function does v have to be?
Constant.
It's got to be a constant function, right? If you take a function of x and y and the derivative with respect to x is 0, there can't be any x's in there. Right? And if you take it with respect to y and it's 0, there can't be any y's in there. Okay, so fine. So if they're both 0, that means there can't be any x's, there can't be any y's. And there's no other variables lying around, so the only thing you have left are constants. So this tells you that v is a constant. Which means that f itself is a constant now. It just sends u is 2 and v is 6. It sends everything to 2 plus 6i. So f is constant. So this means that you look at a function, right? Let's do a precise example. I say something like f of z equals 2 plus say, e to the xi. And I say, is this differentiable?
No.
So it has to be no, because that's a constant. So this has to be a constant. It's not, so it's not differentiable. So the Cauchy Riemann equations rule out a lot of possible functions.
Anyone with a constant?
Anyone that, yeah, when you write in this u and v form, right? If the u is a constant, then you're toast. Now, is there anything special about u? What if v was a constant?
Then you're toast as well.
Well, look, v is a constant, and you know that vx is 0 and vy is 0.
Extra crispy toast.
Run the Cauchy Riemann equations, and you get that ux and uy are 0. And so u must be a constant. So g of z is e to the x plus 2i. Either case, f, g, not differentiable, right? Not analytic anywhere. There's nowhere that they're differentiable. Which is kind of strange. It seemed like nice, reasonable functions. You should be able to differentiate them. Nope, can't do it. So when you can, it must be really important. It must be really cool. Oh, yeah. Any questions? It's a good time to ask one. You're happy? No? You don't know. Let's try to do another thing. What if f of z equals e to the z? Surely e to the z should be differentiable. Come on. That's a beautiful function. Z here is a complex number. And of course we know e to the x is differentiable, that's no problem. But what about e to the z? It's a complex function. Well, to use the Cauchy Riemann equations, right, we need to break it up into this form, u plus vi. So if we write z as x plus yi, right, then this becomes e to the x times e to the yi. And that's equal to, well, you have e to the x, and then e to the yi, remember you can write this as cosine of y plus I sine of y, cis y. And then I can easily break this up as e to the x cosine of y plus I e to the x sine of y. And this is my u, and this is my v. Okay, so if this is going to have a chance to be analytic, then it needs to satisfy the Cauchy Riemann equations. So let's check them. So ux is equal to, so we need to take the partial with respect to x. So the y stuff is just a constant, right? So you just get, well, e to the x, you know the derivative of that is just e to the x. So actually, ux equals u. And uy, now you take the partial with respect to y.
It's e to the x.
E to the x
sine.
of Vx. So with respect to x, again, it doesn't change. E to the x sine y. And Vy, take the derivative of sine, you get cosine, you get e to the x sine of y. And the Cauchy Riemann equations say that if you go from left to right here, they should be the same, and if you go from right to left, they should be negatives of each other. So, look at that. Those are the same, and those are negatives of each other. So, e to the z satisfies Cauchy Riemann. You look perturbed. Looks like a matrix? Yeah, it's Jacobian. I'm intentionally avoiding this, but yeah, this is definitely a matrix.
So could you solve stuff like that using matrices?
Well, there's a place for it. It's not that you solve it, but I mean,
How?
you can write the Cauchy Riemann equations, right, are saying, well, you can write down this matrix. And
If the norm is
if the norm is 1. Well, I mean, you need a matrix where these two things are equal, and these two things here are. So this should be equal, and that should be not equal, but up to a minus.
oh right. Never mind.
Yeah.
It's just for the pattern.
Patterns are good. Okay, now, does this tell you that e to the z is analytic?
No.
No, right? Just says it has a chance. So, the answer to the question of what will be a sufficient condition, which I won't prove that right now. I'll prove it all. I'll tell you one possible sufficient condition. If f equals u plus bi satisfies Cauchy Riemann, on an open set D, and, so there better be an and if ux, uy, vx, vy are continuous, you need continuous partial derivatives, then f is analytic on D. It's differentiable. So if we look at these partials, well, these are all continuous functions. So in fact, since ux, uy, vx, vy are continuous, e to the z is analytic. Just a quick thing we should stop with. If you go back, this is a theorem. If you go back and look at the first example we did, it was something like x plus y squared I, and you look at the partial derivatives, they're all very easy. 0, y, 2y, 1. Those are all continuous functions. So, and at least on that line, y equals 1/2, they satisfied the Cauchy Riemann equations. Right? So they satisfied the Cauchy Riemann equations, and the partials were continuous. But I said no, they're not. It's not differentiable. Exactly right. It's not. They didn't satisfy the Cauchy Riemann equations on an open set. Right? This line y equals 1/2 okay, doesn't give you enough room to maneuver to make an open set. Okay, but e to the z is okay. Okay, so this is really nice. This is one of the highlight theorems of the course. Proving these things about Cauchy Riemann equations, deriving Cauchy Riemann equations. The rest of the week we're going to start looking at some different kinds of functions. Complex functions, complex version of sine and cosine, and the hyperbolic versions, and get the logarithm function, I think. Also, there is a homework online now for the following week. It's homework 3. So enjoy.